In this video I'm going to discuss the theory behind nuclear magnetic resonance spectroscopy, also known as NMR, and I'll also talk about how NMR spectrometers operate. So to begin with, recall from general chemistry that if we take a beam of hydrogen atoms, so we've got some hydrogen atom source, and so I'll represent the hydrogen atoms as little dots. If we fire this hydrogen atom beam through a magnetic field, so this is the north pole of the magnet, and this is the south pole. This is known as the Stern-Gerlock experiment. What we find is, very strangely, half of the hydrogen atoms are deflected towards the north pole of the magnet and half are deflected towards the south pole of the magnet. And we learned that this was the basis for one of our principal quantum numbers for electrons, because electrons have the same property. And that is that certain atoms, certain atomic nuclei, including hydrogen, have magnetic moments that will align in a magnetic field, also known as magnetic spins. And so a magnetic moment will represent with an arrow. So this is an H atom, a proton, nucleus of a hydrogen atom. And the reason it's called a spin is because this magnetic moment is the same sort of moment you would expect from a spinning charge. So if the charge was spinning, we'd produce a magnetic moment. It turns out these atoms really aren't spinning. These magnetic moments are an intrinsic property of hydrogen atoms and certain types of atomic nuclei. But the name stuck, and so we refer to them as magnetic spins. Now these spins orient in all different directions until you apply a magnetic field. In an applied magnetic field, the spins will orient in one of two directions. They'll either orient along the direction of the magnetic field, or they'll line against the magnetic field. And so if this is our magnetic field, I'll represent that with B sub naught. So if we're applying a magnetic field in this direction, some of the protons will orient in the same direction as the magnetic field, and some of the protons, some of these nuclei, will orient their spins in the opposite direction, like so. So one is spin up, we say, and the other is spin down. And this is what's happening in the Stern-Gerlock experiment. Some of the protons are spin up and they're deflected in one direction. The other protons are spin down and they are deflected in the other direction. And this is also what happens in an NMR spectrometer. Before I get to that, I should mention that this is true of any nucleus with an odd mass number. Protons, hydrogen atoms with one proton in them, have a mass number of 1, and so they're NMR active. They have these magnetic spins. So do carbon-13 atoms, which is a minor isotope of carbon, which is the other most common nucleus that is taken advantage of or used in nuclear magnetic resonance spectroscopy. There are other nuclei, too, that aren't as commonly used that have odd atomic numbers, but these are the two most common ones. From this point forward, I'll focus on hydrogen atoms or protons because they're the most common. So in an NMR spectrometer, we apply a very powerful magnetic field to a sample. And so, of course, what happens is that all the protons, well, not all the protons, many of the protons will align in that magnetic field. Some will align with it and some will align against it. So I'll represent that with two energy levels or two energy states. So we have a higher energy level in which the protons, or the nuclei, and I'm going to represent the nuclei now as just little arrows. So these nuclei are all spin down. So that's the higher energy state. In the lower energy state, we have nuclei that are aligned with the applied magnetic field, and so they're spin up. And because this is a lower energy state, there are some more nuclei in this state than there are in the higher energy state. But there's very little difference in energy between these states, and so there is a significant number of protons or nuclei in both energy states. And so, again, the direction of the applied field, I think I'll represent that in red now, is this way. So the spectrometer is generating a very powerful magnetic field. And I'll represent that again as B sub naught in this direction. So we have more nuclei aligned with the magnetic field in the lower energy state than against the magnetic field in the higher energy state. So And so this is also energy that we're representing here. Now we recall again from general chemistry that the difference in energy between two energy states is equal to Planck's constant times the frequency of some applied electromagnetic energy. So nu is frequency here, h is Planck's constant. It turns out that the stronger the magnetic field, the bigger the difference between these two energy states. And so this is the weaker field, we'll say. Weaker magnetic field. B naught being the magnetic field. And so if we have a stronger magnetic field, we'll represent that over here. We have a bigger gap in energy between the two states, between the two energy levels. That corresponds to a higher frequency. So the frequency here for the weaker magnet will be lower than the frequency here for the stronger magnet. Stronger magnets are more expensive, and they correspond to higher frequencies. And so what we're going to find, the basic idea behind NMR spectrometry or spectroscopy, is that we apply the strong magnetic field, and then we apply some electromagnetic radiation that corresponds to this energy gap, this frequency here. So in a weaker field, a common field strength or a common frequency for spectrometers is about 300 megahertz. So this might be a 300 megahertz spectrometer. With a stronger magnetic field, you need a higher frequency. This gap corresponds to a higher frequency, and this might be a 500 megahertz spectrometer. So each nucleus or proton generates its own little magnetic field, its own little magnetic moment here. And when we apply the strong magnetic field, some are spin down, some are spin up, but there's a net excess of spin up versus spin down, lower spin state versus higher spin state. And if we sum all these little magnetic fields from all of these little protons, all these little nuclei, there's a net magnetization, therefore, in the spin-up direction, and I'll represent that with a big arrow. So this is our net magnetization. And again, this is simply the sum of all the little magnetic fields, all the little magnetic dipoles, or magnetic moments of each of the nucleus. So if there's more in the spin-up state than in the spin-down state, the net magnetization is in the upward direction. It's sort of like adding dipoles together, bond dipoles, to figure out the net dipole in a molecule. So with that background, we're now ready to understand how NMR spectrometers operate and give us information, structural information. So here I have a simple schematic diagram of an NMR spectrometer, incomplete at this point. So we have a giant magnet, source, of course, of our magnetic field. The sample is generally placed inside the magnet in a long, thin glass tube, and so the sample here I've represented the compound as this red portion here inside the glass, the yellow glass tube. And the magnet is, in modern spectrometers, is a superconducting magnet. And so the way the magnetic field is generated is you have a big coil that's cooled in liquid helium to very close to absolute zero. And that coil is superconducting at those low temperatures. So you put a little bit of current in here and it just goes around and around forever. And this circulating current, if you take physics, you'll learn that a circulating current like this, an accelerating current, generates a magnetic field perpendicular to the direction of the circulation of the current, which is why we call those magnetic moments on those nuclei magnetic spins, because they're the sort of magnetic moments you would get if those nuclei were actually spinning. And so this circulation of current generates our very powerful magnetic field, which I'll represent again as B sub naught. So it's going up in this direction perpendicular to the coil of the magnet. So there's our magnetic field. Now perpendicular to that magnetic field we have another coil here. In this coil we put current through this coil as well, and this generates RF radiation in this direction of a given frequency, depending on the frequency of the current going through the coil. And so our RF radiation irradiates the sample. RF stands for radio frequency. And so what's happening here? It turns out that when a nucleus is in an applied magnetic field, so here's our proton nucleus again, the magnetic moment is not static. That means it's just not pointing straight up and down. It's actually a little bit tilted. The axis of rotation, or the axis of the magnetic moment, the direction of the magnetic moment is a little bit skewed. The magnetic moment is actually rotating. The term for this is precessing in the applied magnetic field. And so if this is the axis, we can think of this as an axis, this magnetic moment is rotating. So it's really this, when this thing is oriented with or against the magnetic field, this magnetic moment is rotating, it's precessing. It's like a wobbling top on a tabletop. And this precession has a certain frequency. That is, as this arrow, this magnetic moment rotates, precesses, there's a certain number of precessions and a certain number of seconds. So if this were to go around once in 1 second, the frequency would be 1 cycle per second. If it were to go twice in 1 second, the frequency would be 2 cycles per second. That frequency is known as the Larmor frequency. And what happens with this RF radiation, when the RF radiation, the frequency of the applied RF radiation, remember this is our RF, our radio frequency radiation. When the frequency of that applied radiation matches the Larmor frequency, so if this is 1 cycle per second and the Larmor frequency is 1 cycle per second, the two frequencies are in resonance and the nucleus absorbs that RF radiation. And when the nucleus absorbs that RF radiation, that's known as resonance, and the nucleus tilts on its axis. That means that the magnetic moment no longer is applied with the magnetic field, but it's now oriented perpendicular to the magnetic field. It's no longer roughly parallel, precessing, it's now perpendicular to the magnetic field. And so to summarize again, when the RF radiation is in resonance with the precession, the precessional frequency, the Larmor frequency of the nuclei and the aligned nuclei in the magnetic field, those nuclei, and these are the lower energy nuclei, will absorb that RF radiation, causing the magnetic moment to tilt on its axis, like so. And so what does that do to our relative populations of spin up and spin down nuclei? Let's go back up to this. So what that's going to do, since some of these nuclei are no longer in the spin-up direction, we're now going to have the same number of nuclei, I'll do it on both of these and both of these spectrometers, that are in the spin-up direction as in the spin-down direction, like so. When these nuclei down here go into resonance, we now have the same number of nuclei spin down as spin up. So what does that do to the net magnetization? The net magnetization now is no longer in the direction of the applied magnetic field. It's now, since we've tilted some of these nuclei perpendicular to the magnetic field, the net magnetization is now perpendicular to the magnetic field. I think I'll represent that down below. So here is our net magnetization again. We have irradiated this and caused the net magnetization now to be perpendicular to the applied magnetic field. So it's now in this direction. If this is the applied magnetic field, it's perpendicular to it. Now, the thing is, this RF radiation is rotating. That is, it's got this frequency. This could be 1, 2 cycles per second, maybe 1 cycle per second, but there's some frequency to this. And that's pushing this net magnetization perpendicular to the magnetic field, but it's also causing it to rotate. And so I'll represent that here. So there's this rotation of this net magnetic field, this net magnetization of the nuclei. And the frequency of that rotation is the same as the Larmor frequency, which is the frequency of the absorbed RF radiation. And so we have this, and I'll represent that in our spectrometer now. So all the protons, not all the protons, but the protons in the sample, have a net magnetization in a direction that's perpendicular to the applied magnetic field. And so there's our net magnetization. But the RF radiation is causing that net magnetization to rotate, like so. So we have this rotating magnetic field that's the result of the rotating spins of the nuclei. And there's one more coil in the spectrometer. So here is the third coil in the spectrometer. This is known as the receiver coil. Like so. So that's my best effort at a coil. Now, a rotating magnetic field like this, this net rotating magnetization, will generate, and you learn this in physics, will generate a current in a coil. This is how generators operate that make electricity. And so this rotating magnetic field creates a current in this coil, in this receiver coil. And that current is what the spectrometer is detecting. Inducing a current in a coil like this with a magnetic field is known as Faraday induction. And that generates an alternating current. As this goes in one direction, the current goes one way. As it comes back around, the current goes the other way. That's an alternating current. And so with the alternating current, there's an alternating voltage. And so if we plot voltage versus time, we're going to see something like this. So I'll put the voltage on the y-axis, so V for voltage, and time on the x-axis, the time in seconds. And what we see is a cosine wave, like so. Now, modern NMRs are often referred to as FT NMRs. FT stands for Fourier Transform. And what a Fourier transform is it takes time, the x-axis here, and converts it to frequency. So we convert time to frequency. And so let's say that this was 100 cycles per second. So here's one cycle, and this wave goes 100 times in 1 second. So 100, frequency 100 hertz, or 100 cycles per second. So if we convert time to frequency, that means that when we plot frequency on this axis instead of time, we're going to get a single peak known as a resonance. Okay, so we're going to plot frequency versus intensity now. So the intensity that we're talking about here is the amplitude of the voltage. Okay, and so this is intensity, y-axis, and the x-axis is frequency. So we're going to get a resonance, a peak known as a resonance, because this frequency comes from the Larmor frequency, when the RF radiation, the applied RF radiation, was in resonance with the Larmor frequency. So peaks in an NMR spectrometer are known as resonances. And so if this frequency was 100 hertz, we're going to get a peak at a frequency, or resonance at a frequency of 100 hertz. And the intensity of this voltage is what gives us how high this peak is. So this would be, again, 100 hertz. Now here's the key to understanding NMR spectrometry, or spectroscopy, and that is different protons in different parts of a molecule experience this applied magnetic field with a different force. That is, protons in different chemical environments have different magnetic environments. And that alters the gap in between these energy levels, which alters the frequency of the applied RF radiation, which of course alters the frequency that you're detecting in your receiver coil. So a proton in one part of a molecule will absorb a different frequency of RF radiation, which will be picked up in the receiver coil, than a proton in a different chemical environment in a different part of a molecule. And so if we had another proton in a different magnetic environment, in a different chemical environment, we're going to see a different cosine wave. Now this cosine wave has a higher frequency than the first one. So if we compare the two, we see this one is 100 Hertz, and we'll just say that this one's 200 Hertz. Got twice the frequency. Try to get both of those on the same screen. So we'll say that this one is 200 Hertz. At a different Larmor frequency, it absorbed 200 Hertz of RF radiation. And so what we're going to see in our NMR spectrum after we've done our Fourier transform is a peak or a resonance at a different location at a different frequency. So instead of 100 Hertz, we'll see a resonance at 200 Hertz after we've done our Fourier transform. And this is the basic principle by which NMR spectrometers give us structural information. And I'll talk more about this with regard to the two most common types of NMR spectrometry or spectroscopy in the next two videos. The next one will be on proton NMR specifically, and the specific types of information we get from proton NMR spectroscopy. And then the second one, really the third video on NMR, and the last one will be on carbon-13 NMR, which is a little bit different but largely similar. So hopefully this made sense. If it didn't, you can ask me questions about this. And even if you don't have a firm grasp of the theory and behind NMR spectroscopy and how these NMRs operate, that won't prevent you from being able to use this information to determine structures of organic compounds, of organic molecules, which is really the most important skill that I'm concerned with. And that's what the upcoming videos on proton and carbon-13 NMR are about.